Hello everyone and welcome to the coronavirus edition of the second lecture of our signal theory class. In this lecture we will first talk about the characteristics of the deterministic signals, and then we will start talking about the spectral analysis, which I consider to be the first interesting topic of this class. So first we will start talking about the characteristics of the deterministic signals, and the first characteristic will be the average value. Why do we need the average value? Well, let's say that we measure this signal and this signal. They are almost the same except that the second signal is shifted upwards. And now we would like to quantify the difference between these two signals. Well, the easiest way to do this is to compute the average of all the values of these signals. In this case, the average would probably be close to 0, and in this case the average would correspond to the level indicated by this green line. The easiest way how to compute the average value is for discrete signals. In that case, we just sum all the values of the signals and then we divide by the number of added values. So in this case, I'm computing the average in the interval from n1 to n2, so I need to divide by n2 minus n1 plus 1. Each year, it is a mystery to some students why I have this plus 1 here, so let me explain. For example, let's say this n1 is 4, and this n2 is 8. So this interval will include the values 4, 5, 6, 7 and 8. That is 5 values in total. So if here I sum 5 values, here I need to divide by 5. Now let's see what happens if I just had n sub 2 minus n sub 1 here. N sub 2 minus n sub 1 here is 8 minus 4, which is 4. That is not 5, which I want to have here. When I want to do it correctly, I need to compute n sub 2 minus n sub 1 plus 1, which when you crunch the math will give you the required 5. So to compute the arithmetic mean properly here, I need to divide by n sub 2 minus n sub 1 plus 1. So this is how you compute the average value of a discrete signal in the interval from n1 to n2. Now, how do you compute the average value of a continuous time signal? Well, a continuous time signal you cannot sum. Instead, you have to integrate. So for a continuous time signal, we will integrate in some chosen interval from t1 to t2, and then we need to divide by the length of that interval. That will give you the average value of a continuous time signal in the interval from t1 to t2. Sometimes we do not want to know the average value of a signal just in a finite interval, but we want to know the average value of the entire signal. For a discrete time signal, that means the average value for n going from minus infinity to plus infinity. For a continuous time signal, that means the average value for time going from minus infinity to plus infinity. To compute that, we essentially use the same formulas but in a limit. So this is the average value of the entire discrete time signal. First I will sum from minus n to n, then I will divide by the number of values that I have summed, and the entire expression is computed in a limit for n going to infinity. In the case of a continuous time signal, it's very similar. I will integrate the continuous time signal from minus t to t, divide by the length of the interval, and the entire expression is computed in a limit for t going to infinity. And there is all I want to tell you about the average value. Now I will talk about another characteristic of deterministic signals, which is power. What is power good for? Well, let's take these two signals. Just by looking at these two signals, do you see a big difference in the average value of this signal and this signal? It's not a big difference. Both average values seems to be about 0. So these two signals do not differ in the average value much. But just by looking at them, you could say that this one is smaller and this one is bigger. Now, how do we formalize this? Imagine that you would put these two signals to a speaker, in which case the speaker would give you a louder sound. Well, that would be the case of the second signal. Or alternatively, imagine that these two signals are voltage which you put on a resistor. Well, in which case do you think this resistor will create more heat? Again, it will be in the case of this second signal. And this example with the resistor is actually good enough to formalize this. What is heat on the resistor? Well, that is the power lost in the resistor. And when I have a resistor and there is some voltage on this resistor and there is some current flowing through this resistor, how do I compute the power lost on this resistor? Well, that power is the voltage times the current. Also, I can rewrite this using the Ohm's law. Instead of this current, I can use the voltage divided by the resistance. And when I write it like this, I can also rewrite it like this. So when I square the voltage and divide it by the resistance, I will get the amount of power flowing to the resistor. But in the case of a generic signal, we do not have a resistor. But we do like the concept. So we imagine that we put this signal on an imaginary resistor, which for the sake of simplicity we say is equal to 1, and in this case the power will be given by the signal squared. In fact, this is the power flowing into that imaginary resistor at the instant given by this time t, and that is the reason why we call it the instantaneous power. We define the instantaneous power as the signal squared. This absolute value comes into play if the signal is complex. In that case, you need to have the absolute value squared. And this is the definition for the continuous time, and this is the definition of the instantaneous power for the discrete time. Sometimes we are not really interested how the power changes from 1 millisecond to another, but we would like to know the average power in some interval. Where in that case, if we want to know that average power, we just compute the average from the instantaneous power. And that is how the average power is defined for continuous time and for the discrete time. For power in some finite interval, we will usually use this symbol P. And we will use this symbol P sub infinity to denote the average power of the entire signal. That is for the continuous time signal when time is in the interval from minus infinity to infinity, and for the discrete time signal where the n is going from minus infinity to plus infinity. Another characteristic I will tell you about is energy. The energy is pretty intuitive. When you have some load and you feed it some power, then when you sum up that power over time, you will get the amount of energy that you have fed into that load. So mathematically, the energy is defined as the integral of the immediate power over time. And we are integrating over some chosen time interval that I have denoted as this scripted I. When for the power I substitute this definition as the signal squared, I will get this expression for the energy. And when we are dealing with the discrete time signal, the energy is defined as the sum of the immediate power over some chosen time interval I. When for the immediate power I substitute its definition as the signal squared, I will get this expression for the signal's energy. The energy in some finite interval we will denote as E. This E sub infinity we will use to denote the total energy of the signal. That is the energy in the interval from minus infinity to plus infinity. That is what I will call the total energy of a signal. Now, using energy and power allows us to do another classification of the signals. A signal is called a power signal if the average energy of the entire signal is finite. On the other hand, a signal is called an energy signal if its total energy is finite. Sometimes the power signals are also required to have their total energy infinite. In that case, you cannot have a signal that is both energy and power. An example of an energy signal would be this pulse. When you square this pulse and integrate it in the interval from minus infinity to infinity, you are going to get some finite number. Thus, this signal is an energy signal. An example of a power signal would be this sine. If you square this sine and try to integrate it from minus infinity to plus infinity, you are not going to get a finite number. Thus, this cannot be an energy signal. But if you square this signal and then compute the average, you are going to get some finite number. So this signal is a power signal. So the average value, power and energy were characteristics of a single signal. But sometimes we need to assess similarity between two signals. What is this good for? Well, in signal processing we oftentimes have several templates and we measure a signal and we want to find out to which of these templates that measured signal is the most similar to. For example, this would be used in speech recognition. We would have some templates of several words, we would try to record a spoken word, and then we will try to match to which of our templates is the spoken word the most similar to. In that way, we would find what is the word that was spoken. For speech recognition, the measures of similarity are fairly complicated. We will not use those. We will use a fairly simple measure of similarity, which is called the mutual energy. How does it work? Here I have two cases, one case of similar signals and one case of dissimilar signals. Here I have a signal x1 and very close to it I have a signal x2. This is the case of similar signals where signal x1 and x2 are close to each other. Here, the signal x1 and the signal x2 are noticeably more different. Now, how could I mathematically quantify that these two signals are more similar than these ones? Well, for that, I could use the area in between these signals, the area which I have cross-hatched here. In the case of the similar signals, this area will be small, and in the case of dissimilar signals, this area will be big. So this area could serve as a measure of similarity, but in reality we do not use it. More often we use something which can be derived from the idea of this area. Let me show you the derivation. This is a mathematical way how to express this area. What I do is that I take one signal, I subtract the other, I take the absolute value of the difference, and then I integrate within some chosen interval I. The resulting area A would be small if the signals are similar, and it would be big if the signals are different. So you could use this as a measure of similarity, but it turns out that when you start using it, the mathematics is not very nice. And it turns out that it gets nicer if you do not just use the absolute value, but you use the absolute value squared. The reason behind this, without getting into too much detail, could probably be related to the fact that the absolute value itself is not a smooth function, it has a discontinuous derivative at 0, but in contrast, the absolute value square is a very nice smooth function, and that gives us nicer maths when we start to take derivatives. But as a measure of similarity, this expression is not going to be that much different from this one. If these two signals are similar, then we are going to have small values here, and the entire value of this integral is going to be small. And if these signals are dissimilar, then this difference is going to be big, and the value of this integral is also going to be big. Now, this is still not the final expression for the measure of similarity. To get that mutual energy which I want to get to, we need to make some alterations. So first, I will apply this square, which, at least for real signals, will give me this. Here, I will apply this integral to these individual summands. That will give me this. And here, using what we have learned on the previous slide, we can identify that this first integral is in fact just the energy of the signal x1, and this second integral is in fact just the energy of the signal x2. Now, if I want to measure the similarity between the signals x1 and x2, will the energy of the signal x1 tell me anything about its similarity? Well, it can't. It's just a characteristic of the signal x1. It does not know anything about the signal x2. So this does not tell me anything about a similarity, therefore it is not interesting. The same argument here. Does the energy of the signal x2 tell me anything about the similarity between those signals? No, it is just the characteristic of the signal x2. It does not know anything about the signal x1. Therefore, this does not tell me anything about a similarity, and it is not interesting. In fact, the only expression that tells me something about the similarity between the signals x1 and x2 is this one. And this expression we call the mutual energy of the signals x1 and x2. I will denote it as E sub 1, 2. Now, what are the values of the mutual energy if the signals are similar and dissimilar? To illustrate this, I took this case of the similar signals and I shifted this signal x2 to the right. That gave me this case where the signal x1 is the same, but the signal x2 was shifted to the right by some amount of delta, and that gave me the new signal x2. This is the new shifted signal x2. Now what happens when I move from here to here? Well, the signals are less similar in this case. This area gets bigger, so the value of this integral should get bigger as well. But does the energy of the signal x1 changes? No, we did not change the signal x1. Does the energy of signal x2 changes? No, we just shifted the signal. It has the same energy. So the only thing that changes in this case is actually the mutual energy. And how does it changes? Well, if this gets bigger and this does not change, then the mutual energy must be getting smaller because it has the negative sign in front of it. So if the signals are getting more and more dissimilar, this area is getting bigger, the value of this integral is getting bigger, and the value of the mutual energy is getting smaller. Thus, dissimilar signals will give us smaller mutual energy. And in the opposite direction, if I start here and I would move this signal back to this position, I would get more similar signals. That would mean that this area would be smaller. That would also mean that the value of this integral would be smaller. This still would not change, and consequently the mutual energy would have to get bigger. Thus, when I get more similar signals, the mutual energy gets bigger. Here you have it summarized. If we have similar signals, the area in between the signals is getting small and the mutual energy is getting large. If we have dissimilar signals, the area in between the signals is getting large and the mutual energy is getting small. So those similar signals will give us large mutual energy and dissimilar signals will give us small mutual energy. At this point, you might have a feeling that the mutual energy is not an ideal measure of similarity, and that is true. But it is simple and mathematically convenient, so we like to use it. Thus, this is the definition of the mutual energy, our new measure of similarity. This is the definition of the mutual energy for discrete signals. It's pretty much the same, except instead of integration, now you have summation. In addition to the mutual energy, you can also have the mutual power. The definition of the mutual power is pretty much the same as the definition of the mutual energy, but in addition to this interval, you will also divide by the length of that interval, and that will give you the mutual power. This is the definition of the mutual power for the discrete signals. The only difference between the mutual energy and the mutual power is really just this scaling. So it's pretty much the same thing. Now, in addition to these formal definitions, I would also like to show you the geometric interpretation of the mutual energy for discrete signals. This is the mutual energy of the signals x1 and x2 computed in the interval from 1 to n. Now, I will take all the values of the signal x1, that is the value for n is equal to 1, the value for n is equal to 2, all the way to the value for n is equal to the capital N, and I will write these values as a vector, which I will denote like this. And I will also take all the values of the signal x2 and I will write them as a vector, which I will denote like this. And when I have these two vectors, note that I can actually write this sum as a dot product of these two vectors. This sum is nothing else than a dot product of these two vectors. So I can imagine that my signal x1 is some vector in an n-dimensional space, and so is my signal x2. Now, if my signal x1 is similar to the signal x2, these two vectors point roughly into the same direction. In that case, the dot product of these two vectors is large. The dot product of these two vectors is large. The mutual energy is large when those signals are similar. In contrast, if my signals are dissimilar, these vectors point in different directions. For example, here I have a case where they are perpendicular to each other. In that case, the dot product of these two vectors is 0. So if my signals are dissimilar, these vectors point in different directions, their dot product is small, this dot product is small, and that corresponds to the mutual energy being small as well. If the signals are dissimilar, the mutual energy is small. So the moral of the story is that the mutual energy corresponds to the dot product between two vectors. And this also leads us to the definition of the mutual energy for complex signals. You probably know that when these two vectors have complex values, we do not compute their dot product like this, but we complex conjugate this second term. So when we define the mutual energy for complex signals, we do it like this. It's almost the same as what we had before for the real signals, but the second term is complex conjugate. And this goes for the discrete signals. For the continuous time signals, it's almost the same, but we have integration instead of the summation. Okay, now we have the boring basic stuff behind us and we can start doing something interesting. And the first interesting thing that we will do will be the spectral analysis with the Fourier transform. First, let me explain intuitively. I have a speaker and I let that speaker play a sound. When I record that sound with a microphone, I get this signal. It is actually a sine wave with period of 1 millisecond and frequency of 1 kilohertz. However, when you listen to that sound, you did not perceive that the pressure of the air was increasing and decreasing 1000 times per second. The way you perceived that sound was that that sound had some pitch, some frequency, and it had some intensity. In fact, if you were trained to have absolute pitch, you would even be able to tell what that pitch, what that frequency of the sound is. Most of us cannot do that, but what most of us can do is to perceive the change in frequency and intensity. Let me demonstrate with another sound. When I record this sound with a microphone, I will get this signal. This signal is again a sine wave, but it has the frequency of 1.5 kilohertz and it has half the amplitude compared to the first signal. However, even now you did not perceive that the air pressure would increase and decrease 1500 times per second. What you did perceive when you listened to this sound was that it was at a higher frequency and it had lower intensity. Now listen to this sound. If you recorded this sound with a microphone, you would get this waveform. Actually, this sound was created by summing these two signals together and playing them. When you sum this signal and this signal, you will get this. Now, it is very difficult to tell by just looking at this waveform that it is actually composed of these two signals. But if you had a musically trained ear and you would listen to this sound, you would be able to tell me that this is actually a chord of a perfect fifth. And a chord of perfect fifth contains a bass note and a note which has frequency 1.5 times higher. So the moral of this story is that when we listen to sound, we cannot perceive how the air pressure changes in time. What we perceive is the frequency and intensity of that sound. These were examples of very simple sounds. When we have a sine wave, we call that a pure tone because it contains only a single frequency. And when we combine two pure tones at different frequencies, we can get a chord, which in this case contains only two frequencies. Now, what would happen if you listened to something more complex? For example, if I played you sound ah. If you recorded this sound with a microphone, you would actually get a signal that looks like this. But again, if you listen to it, you do not perceive those fast changes of the air pressure. What your ear actually does perceive is a fairly complex combination of intensities at different frequencies. Now, your brain actually has this information at its disposal, but it does not present you with this plot. Instead, your brain looks at those intensities at different frequencies, and based on that, to your conscious mind comes the information about what has been said. So in this case, based on the analysis of the intensities at different frequencies, your brain tells you that it is sound "ah" that has been said. So overall, there are these two ways how to present a signal. You can either specify how the values of the signal are changing in time, or you can say which frequencies the signal contains and what are their intensities. This is how a microphone would record it, and this is how signals are being recorded by our ear. When we work with these time courses of the signals, we say that we are in the time domain. When we work with these plots of intensities at different frequencies, we say that we are in the spectral domain. In the time domain, we refer to these plots as signals, and in the spectral domain, we call these plots the spectra of the signals. Now, if you want to analyze a signal, for example, for the purpose of speech recognition, you may want to transform it from the time domain into the spectral domain. For that, you would need a mathematical equivalent of your ear. And this mathematical equivalent actually exists. When you want to take a signal in the time domain and turn it into the spectrum in the spectral domain, the mathematical ear that you can use is called the Fourier transform. And you can also do the opposite. If you had a spectrum in the spectral domain and you would like to turn it back into a signal in the time domain, you could use what is called the inverse Fourier transform. Now let me give you a more specific but still a fairly rough idea what the spectral analysis with the Fourier transform does. We imagine that a signal in the time domain is composed of a spectrum of tones, each of those tones at different frequency. A tone at each frequency f we imagine in this form. It is a cosine with some amplitude specific for that frequency f and also some phase, again specific for that frequency f. In this first approach I did not mention the phases, but for the stuff to work they need to be there. Now these amplitudes and these phases are chosen so that when we sum up the individual tones we get our signal. This is how I can write it mathematically. When I take my tones with properly chosen amplitudes and properly chosen phases and I add everything together, I will get my signal. So now I can say that my signal is composed of these tones, of these frequencies. And what the Fourier transform does, the Fourier transform takes my signal, and from that signal it will tell me what are the amplitudes and phases of those individual tones. What are the amplitudes and phases at the individual frequencies? Actually, there are 4 types of the Fourier transform. And the first type of the Fourier transform we will study in greater detail is the Fourier Series. We will deal with signals that are periodic with period t and frequency 1 over t. And the Fourier Series is actually the Fourier transform for the signals that are periodic. We will build the Fourier series in some smaller steps, and the first steps will be to find which frequencies are going to be contained in a signal that has the period t. To examine this, let's take a look at a couple of sine waves. The first sine wave, which I denote as x1, has a period of t. This interval is the period which repeats itself. But do not forget, even though the signal x1 has the period of t, it is not the only period. This interval will also repeat itself, and this interval, if the entire signal is a sine, will also repeat itself. So the signal x1 has a period t, but it also has periods 2t, 3t, 4t, and so on. Now, let's take a look at the signal x2. The signal x2 is also a sine, but it has twice the frequency of this signal, so its period is going to be half of this one. The period of the signal x2 is going to be t over 2, but again it is not the only period. This signal is also going to have the period of t, 3 over 2t, 2t, and so on. These periods in this plot correspond to this interval, which has the length of t, this interval, which has the length of 3 over 2t, and this interval, which has the length of 2t. Now, what happens if I add the signal x1 and the signal x2? Well, specifically for these two signals, I'm going to get this signal. And because both signal x1 has the period of t and the signal x2 has the period of t, the result will be periodic with the period of t. You can even see it here. In both signals, the blue interval is the same as the red interval, and that is the same as the yellow interval. Now, what happens when I include this signal x3? The signal x3 is some phase-shifted sine wave which has the frequency 3 times higher than this signal. That means the period of the signal x3 is t over 3. But again, this is not the only period. This signal is also going to have the period 2 over 3 times t, t, 4 over 3 times t, and so on and so forth. Now, what happens when I add all these three signals together? Well, I get this. And you can see that the result is still periodic with the period of t. Well, that makes sense. This signal repeats itself with a period of t, this signal repeats itself with the period of t, and this signal also repeats itself with the period of t. So when I add them, the result should repeat itself with the period of t. Now, here comes the twist. Here I added a signal x4, and this sucker has the frequency which is 1.7 times higher. That is the frequency of this signal x1. So its period is going to be t over 1.7. And again, this signal does not have only this period, but it's going to also have these periods. But none of these periods is t. You can even see it in this plot. The blue interval is different from the red interval, and that is different from the yellow interval. This signal does not repeat itself with a period t. So what happens when I sum all these signals together? Well, in this specific case, I will get this result. And this signal is no longer periodic with the period of t. You can see that the blue part of the signal is different from the red part of the signal, which is different from the yellow part of the signal. That is all because of this signal, which is not periodic with the period t, so when I added it to these signals, the final sum lost the periodicity with the period t. The moral of the story is that if I'm going to express my signal as a sum of a bunch of pure tones, then if my signal has a period of t, then these functions, these tones also need to have the period of t. If any of these tones does not have the period of t, the periodicity of my signal will be broken. Thus, my signal will contain pure tones either with period t or the period t divided by some integer. My signal is going to contain tones with periods t or t divided by some integer. That means that my signal is going to contain pure tones with frequencies f, 2f, 3f, 4f, and so on. My signal is going to contain frequencies which are the integer multiple of the fundamental frequency. So here I have the answer to my question, which frequencies are going to be in the signal which has the period of t. This signal is going to have the frequencies which are the integer multiple of its fundamental frequency. So from the previous slide, a periodic signal with a period t and frequency f is going to contain frequencies f, 2f, 3f, 4f, and so on. The signal is going to contain the frequencies which are the integer multiple of the frequency f. That frequency f we call the fundamental frequency, and higher multiples of that frequency we call higher harmonics. Also, these frequencies correspond to the periods which are integer divisions of the period t. That period t we call the fundamental period. With this knowledge, we can specify the generic idea that our signal is composed of different tones at different frequencies. Now we know that the individual tones are going to have the frequency which is the integer multiple of the fundamental frequency. So instead of using some generic frequencies omega and summing through them, we can actually use the frequencies 2 pi kf, where that f is the fundamental frequency and this k goes from 0 to infinity. This interval from 0 to infinity will create all these multiples of the fundamental frequency and also the zero frequency. The zero frequency I will get when k is equal to 0. When that happens, when 0 is here, this cosine is just a constant, and that will allow us to include into this sum any constant that can be included in this signal. And one more thing, this 2 pi kf is often written as omega sub k. That is, omega sub k is equal to this, and if we use the period instead of frequency, we can write it as 2 pi k divided by the fundamental period. So thus far we know that a periodic signal contains these tones, and when we sum those tones, we get our periodic signal. The sum of all of these tones we call the real Fourier series. And of course the elephant in the slide is that we still do not know what are the amplitudes and the phases of these individual tones. That we will find on the next slide. Before we do that, I still need to complicate things a little bit. I need to rewrite this real Fourier series into what we call the complex Fourier series, where these cosines are written as complex exponentials. That will give you some head scratching now, but it will save you some troubles later. So I need to take these cosines, these pure tones, and write them as complex exponentials. That is what we did on the lecture 1, and there I showed you that you can take this cosine and write it using two complex exponentials like this. The amplitude and the phase of this cosine will come to this complex amplitude and this complex amplitude like this and this. And this frequency will come to the argument of this complex exponential and this complex exponential. Now when I express each cosine, each pure tone at each frequency in this form, I can actually rewrite this Fourier series into this form. Let me explain how that is done. First note that now the index k goes from minus infinity to plus infinity. To give you a better idea what this sum looks like, here I have written down a couple of summands from that sum. So this is the summand for k is equal to minus 3. This is the summand for k is equal to minus 2. This is the summand for k is equal to minus 1. Here the k is 0, 1, 2, 3. Now note that for positive k, that is for k 1, 2, 3, here I'm summing these parts of these cosines. So these parts of these cosines are included in the sum for k positive. Now what about these summands for k negative? Well, I cannot take those directly from here, because this expression, that is this expression, which is this expression, is not used for negative k. There are no negative k's in this interval. But what we can do is that we will define that c minus 1 is equal to c sub 1 complex conjugate. And we will also define that omega with the index minus 1 is equal to minus omega 1. When we do this definition and this definition, this expression will turn into this one, which actually corresponds to this part of this cosine for k is equal to 1. In similar fashion, we will deal with the other negative case. In this case, when k is equal to minus 2, we will define that c with the index minus 2 is equal to the c sub 2 complex conjugate, and omega with the index minus 2 is equal to minus omega sub 2. When we do that, this summand will turn into this one, which actually corresponds to this for k is equal to 2. The same story goes here. This is how we define c sub minus 3, and this is how we define omega sub minus 3. When we do that, we get this, which corresponds to this for k is equal to 3. So for negative values of k, we will define these complex amplitudes and these frequencies so that these summands correspond to these parts of these cosines. So these parts of these cosines will be included in this sum when k is positive, and these parts of these cosines will be included in this sum when k is negative. And formally, these definitions for negative k we can write like this. When k is negative, the omega for that negative k will be minus omega with subscript that is now positive, and c for k that is negative will be the complex conjugate of the c with the same subscript except positive. Also check out this. When I take this summand and I add this summand, that is when I add this and this, I will essentially get this expression for k is equal to 1. So the result will be this for k is equal to 1. And when I add up this summand and this summand, that is when I add up this and this, I will get this expression for k is equal to 2. So the result will be this for k is equal to 2. And once more, when I add up this summand and this summand, that is essentially when I add this and this, I will get this for k is equal to 3, which is equal to this for k is equal to 3. So this way, these cosines are hidden in this series. And the bottom line is that I can take this real Fourier series, which is kind of intuitive, and I can rewrite it into this form. This form is less intuitive, but it is more concise and it is mathematically easier to work with. So this form is usually preferred. It is called the complex Fourier series, and that is what we will work with. These complex amplitudes c sub k are called the coefficients of the complex Fourier series. At this point, it is important not to forget what we are working with. Here, we are just basically saying that our signal contains some pure tones at these frequencies, and when we use proper complex amplitudes, that means that when we use the proper amplitudes and phases of these cosines which are actually hidden in here, then when we sum everything up, we will get our signal. That is all that is being said here. What we still miss is the way how to find these complex amplitudes, that is how to find these amplitudes and these phases of these cosines. That is what we will do on the next slide. So in this slide we will learn how to find these complex amplitudes. On the previous slide, I told you that this expression, as cryptic as it is, means that my signal contains some pure tones at the frequencies omega k, and when I sum those pure tones together, I will get my signal. Another way how to look at this expression is that my signal is composed from these complex exponentials which have these complex amplitudes, and when I sum those together, I will get my signal. So how do we find what are those complex amplitudes, or what are those amplitudes and phases of those real cosines? Well, the idea is that we will evaluate the similarity between our signal and these complex exponentials at various frequencies omega k. This also means that we would be comparing our signal to the cosines and sines at the frequency omega k, which constitute this complex exponential. Now, why would this work? Well, let me give you a trivial example. Let's say that my signal contains a pure tone at the frequency, for example, 1 kHz. Now I will start to compare my signal with that pure tone at 1 kHz with complex exponentials at different frequencies. That means that I am comparing my signal with cosines and sines at different frequencies. Now, if my measure of similarity works properly, it should not indicate any similarity between my signal and these cosines and sines unless this frequency omega k is that 1 kilohertz. Moreover, that measure of similarity that we will use will get bigger when the amplitude of my signal will get bigger. And on top of that, I will be comparing my signal to a cosine and the sine at that frequency of 1 kilohertz. And depending on whether my signal is more similar to a cosine or a sine, I can get an information about the phase of that 1 kilohertz node in my signal. And this is what happens when there is only one tone in my signal. If there are multiple tones in my signal, basically all of this stuff happens, but for each tone separately. So if I find out that there is a big similarity between my signal and the cosine and sine at the frequency of 2 kilohertz, well, that indicates that my signal contains something at 2 kilohertz. And the bigger the similarity, the stronger the content at those 2 kilohertz. And on top of that, I can get some indication about the phase of the 2 kilohertz content when I check whether it is more similar to a cosine or a sine at 2 kilohertz. Now, how do we evaluate that similarity between my signal and the complex exponentials at the individual frequencies? Well, we did have one measure of similarity, and this is where the mutual energy comes in. To evaluate the similarity between my signal and this complex exponential, we will compute their mutual energy. This is the mutual energy of my signal and that complex exponential. This minus is here, but it is not here. The reason is that when we compute the mutual energy between complex signals, and this complex exponential is a complex signal, we need to take the complex conjugate of this second signal, thus this minus. And these integration limits are set over one period, which kind of makes sense for a periodic signal. All the information about the signal is hidden in one period, so it doesn't make sense to integrate over a longer interval. So again, this is the mutual energy, the measure of similarity between my signal and the complex exponential, and now we need to start crunching to evaluate this in some meaningful way. So the first thing that we will do is that we will take this expression and we will substitute that here. That will give us this. In this expression, I would point out that whilst in here I was using k as the index I was summing over, here I changed that index k into letter L. The reason is that this k, that is this k, is completely different from this k. This value can be completely different from this value. So not to get these two k's mixed together, here I used a different letter in this sum. Now, I will change the order of the integration and summation. As long as this sum converges, I'm allowed to do that. And when I change the order of these two operations, I will get this. Here I need to realize that this complex amplitude, this c sub L, is just a constant for this integral, so I can pull it out of the integral. When I do that, I will get this. And here I should realize two things. The first one is that this entire expression is actually the mutual energy between this exponential and this exponential. It is the mutual energy between two exponentials at different frequencies. One is omega sub k, the other is omega sub L. The second thing I should realize is that I can combine these two exponentials into a single exponential. That will actually help me to evaluate the value of this integral. And I do want to evaluate the value of this integral. In fact, I will do it for these two cases. The first case is quite trivial. Here the L, that is this L is equal to k, that is this k. That means that omega L is equal to omega k. The frequency of this exponential and this exponential is the same. That means that this exponential, that is this exponential, actually has 0 in its exponent. That means that this exponential is equal to 1. This exponential is equal to 1. The product of these two exponentials is equal to 1. And that means that this entire integral is just integrating number 1 in the interval from 0 to t. That makes its value equal to t. So when L is equal to k, when this L is equal to this k, the value of this integral is t. Now let's take a look at a slightly less trivial case where L is different from k. Here the frequency omega sub L will be different from the frequency omega sub k. This frequency will be different from this frequency. Therefore, this integral, that is, this integral, will no longer be integrating just 1. This will no longer be equal to 1. But we can still make some simplifications. I can take this difference of these two angular frequencies and rewrite them using the integer multiples of the fundamental frequency f. Remember from the previous slide, omega sub k can be written as 2 pi k times f, where this f is the fundamental frequency and this k is an integer. So here I will be writing 2 pi f times L to express this frequency omega sub L and 2 pi f times k to express this frequency omega sub k. And then when I take this difference, I can write it like this. And this I will use when I will express this complex exponential as a sum of a cosine and j times sine. This will give me the frequency of this cosine and this sine. So it would seem that this integral actually integrates this cosine in the real part and this sine in the imaginary part. Moreover, this k and this L are integers, so their difference is also going to be an integer. Thus, the frequency of this cosine and also the frequency of this sine is going to be an integer multiple of the fundamental frequency. And this can help us to evaluate what this integral is equal to. We need to realize that if this cosine and this sine have frequency which is an integer multiple of the fundamental frequency, then within the interval from 0 to the fundamental period, both this cosine and this sine are going to have the whole number of periods. Let me demonstrate this on a plot. Well, here I have a cosine which has the frequency 3 times higher than is the fundamental frequency. Thus, the period of this cosine is going to be 1/3 of the fundamental period. If this is the fundamental period, then this cosine has a period which is 1/3 of the entire fundamental period. And within this fundamental period, you can fit 3 whole periods of this cosine. Now, if you can fit the whole number of periods within this integration interval, do not forget that we are integrating from 0 to t, then this positive area is going to be exactly the same as this negative area. And the integral over this function is going to be 0. And this is going to hold for every integer multiple of the fundamental frequency for both cosine and the sine. The only exception would be when k is equal to L, but that is not the case which we are dealing with here. So as long as the L is different from k, this integral will always be equal to 0. So this integral can have two values. It can have the value of t, and that will happen when L is equal to k, that is when this frequency and this frequency are the same. But if these two frequencies are not the same, if L is not equal to k, then our integral, this integral, will be equal to 0. Consequently, this entire expression I can write like this. Instead of this integral, I will use t if L is equal to k, and I will use 0 if L is different from k. Now, what will that do to this entire expression? Well, in this expression, I'm summing through L. And unless that L is equal to some chosen k, this expression is equal to 0, so I'm mostly summing up 0. The only summand that is not going to be 0 is the one when L is equal to k. When this L is equal to k. In that case, this expression is equal to t. Thus, this entire sum will be equal to t times c sub k. So the moral of the story is that when I evaluate the similarity between my signal and a complex exponential at the frequency omega sub k, that is when I compute the mutual energy between my signal and the complex exponential at the frequency omega sub k, I will actually get the complex amplitude for the index k, that is, this complex amplitude for the index k. Yes, in this expression I still have this multiplication by the period, but I can take this value and divide it by the period, which will give me the complex amplitude for the index k, and that is exactly what I was after. So when I want to find this complex amplitude for some index k, I need to compute the mutual energy between my signal and the complex exponential at the frequency omega sub k. I need to compare these two signals. And then, when I divide by the period, I will get the value of my complex amplitude for the index k. I summarized that here. My complex amplitude for the index k will be 1 over the period times the mutual energy between my signal and the complex exponential at the frequency omega sub k. Also here I have explicitly written down what is the value of this angular frequency omega sub k. So this is how you compute those complex amplitudes. And because those complex amplitudes also contain the information about the amplitude and phase of the individual tones that constitute our signal, this is also how you transform your signal into these amplitudes and phases. So this expression is actually that mathematical ear that will turn my signal in the time domain to its description in the spectral domain. This is that mathematical ear that will turn my signal from the time domain to the spectral domain. This is one of the types of the Fourier transform. As I told you on the previous slide, these complex amplitudes we call the coefficients of the complex Fourier series. We also call them the complex spectrum of the signal x of t. And when we take the absolute value of the complex spectrum, we will get this magnitude. That is, we will get the information about the amplitudes at the individual frequencies. Thus, the absolute value of the complex spectrum is called the amplitude spectrum. In this slide, I was essentially drawing amplitude spectra of these signals. Here you have the information about the amplitude of the tones that constitute these signals. And in similar fashion, when I take the phase of the complex spectrum, that is when I take this phase, I will get the information about the phase of those individual tones. Thus, the phase of the complex spectrum we call the phase spectrum. So to summarize, thus far we have learned that this is the complex Fourier series. These are the coefficients of the complex Fourier series, which we can compute in this manner. Also, I can talk about these formulas like this. This formula will take my signal in the time domain and it will turn it into the complex spectrum of my signal. And this formula will take that complex spectrum and turn it back into my signal in the time domain. So essentially, this is one of the types of the Fourier transform, and this is one of the types of the inverse Fourier transform. This Fourier transform was constructed for continuous time periodic signal. On the next lecture, we will also have Fourier transforms that are constructed for discrete signals and for aperiodic signals. But we will not go into that right now. Right now, it's time to take a look how we use all of this in an example. Here I have a definition of a signal, and I would like to perform the spectral analysis of this signal. I would like to find out which frequencies it contains and what are the amplitudes of the tones at these frequencies. First, let's take a look at what kind of signal we are dealing with. Here I'm saying in the language of mathematics that I'm dealing with a periodic signal with period equal to 4. Here I'm defining what that signal is within one period. Before we start to analyze the signal, the first thing we always need to do is to plot the signal. Oftentimes the students are lazy to plot the signal and then they screw up everything they can. So what is the plot of this one period of my signal? Well, here I have a difference between two unit steps and that will give me this pulse. Sometimes students do not understand how a difference between these two unit steps can give me this pulse. So I will explain that here in greater detail. First, let's take this unit step, which I have drawn here in red. Then, let's take this unit step, which I have drawn here in green. And now we need to subtract the second unit step from the first unit step. So we will subtract the green unit step from the red unit step. Let's take a look at what happens. Here in this interval I will be subtracting 0 from 0, so that will give me 0. In this interval I will be subtracting 0 from 1, and that will give me 1. Last, in this interval I will be subtracting 1 from 1, which will give me 0. That will give me this 0. So when I subtract these two unit steps, they will give me this pulse. And this pulse is how I define one period of my signal. This is the definition for t within the interval from minus half the period to half the period. That is within this interval, which has the length of the entire period. So this is one period of my signal, and here I am saying that that period with the length of 4 will repeat itself. So this will repeat here, and that it will continue to repeat. Now that we know what our signal looks like, let's analyze it. Let's find out what is its complex spectrum. What are the amplitudes and phases at different frequencies? Well, for that I will need to use this formula for the coefficients of the complex Fourier series. But before I use this formula, I will show you one trick that can make the computation of this integral easier. In this case, I should be integrating from 0 to t, and my period, is 4. So I should be integrating from 0 to 4. But in reality, it doesn't have to be this exact interval. Note that the values in this interval are the same as the values in this interval. That is because the signal is periodic. So integrating my signal over this interval will be the same as integrating my signal over this interval. So I can pick any interval I want as long as it has the length of one period. So I can integrate from 0 to the period, or I can integrate from minus half the period to half the period, or this is how we write it in general, we can integrate over any interval with the length of the period. Just pick whatever is the most convenient for you. Okay, now let's evaluate this integral. Here I have written it again, and here I have copied it, and I have chosen my integration limit to go from minus half the period to half the period. I will be integrating within this interval. Now, when time is greater than minus 2 and less than minus 1, my signal is 0. This is 0, so this entire expression will be 0, and I do not need to integrate it. The same goes for time within this interval. Here my signal is 0 again, so this is 0, this entire expression will be 0, and I do not need to integrate over this interval as well. All I need to do is to integrate over this interval, from minus 1 to 1. Thus I can rewrite this integral into this form. Here I have substituted 4 for the period, and here I'm integrating only from minus 1 to 1. And what am I integrating? Well, for my signal, I need to substitute this value of 1. That is here. And of course, I need to copy this exponential. That is here. Now this integral is very easy to evaluate. It is this. The only thing I need to be cautious about is the division by this omega k. I cannot divide by a 0, so this omega k must not be equal to 0. The omega k must be different from 0. That means that the k itself has to be different from 0. When that happens, my integral is this, which I can also write like this. Here you should be able to identify that the combination of these two complex exponentials will give you this sign. Now I will substitute that the omega k is 2 pi k over t. Or when I substitute that t is 4, I will actually get that this is pi k over 2. And after this substitution, I will get this result. Now, what does this equal to? Well, first note that these two suckers will cancel each other out, so what I'm left with is this sign divided by pi times k. Now, let's take a closer look at this sign. If I plot sine of pi over 2 times t, I will get this function. Now here I'm looking at that function when k is integer, so I will be looking at this function at values like 0, 1, 2, 3, 4, 5 and so on. What will that give me? Well, that will give me these green dots. And note that for k even, that is the values 2, 4, 5, 8, 10, these green dots are always 0. So this expression will be equal to 0 when k is even. When k is odd, the value of this sign will be either plus or minus, and these values will alternate. Mathematically, I can write that like this. For k odd, this sign is equal to this. So these are the values of the complex amplitudes of my Fourier series. That is, when k is different from 0. When k is equal to 0, we need to compute this separately, and this computation is usually fairly simple. So we need to compute the complex amplitude for k is equal to 0. That means that we need to evaluate this integral for omega k equal to 0. That will make the argument of this exponential 0, which will make the value of this entire exponential equal to 1. Thus we need to evaluate this integral. And this integral is nothing else than the average value of our signal computed over one period. You can go ahead and try to evaluate this analytically, but usually just by looking at this picture I can tell that the average value is going to be 1/2. So this is 1/2. The complex amplitude for k is equal to 0 is 1/2. Now that I have computed all the complex amplitudes, I can write down what is the Fourier series of my signal. In the Fourier series of my signal, the k will go from -infinity to +infinity. But because the complex amplitudes are 0 when k is even, I will include only k that are odd. Also, to avoid dividing by 0, from this sum I will exclude k when it is 0. For these values of k, I can use this value for the complex amplitude. So this will come here. And this exponential will come here. Here I have just rewritten the omega k as 2 pi k divided by the period. And last, I must not forget to include the value of this summand for k is equal to 0. That is what I have cautiously excluded from this sum. For k is equal to 0, the value of the complex amplitude will be 1/2, and the value of this exponential will be 1. Why? Because for k is equal to 0, the omega is 0, thus the value of this entire exponential is 1. So for k is equal to 0, this entire expression will be equal to 1/2, and that is what I have here. So this entire expression is the Fourier series of my signal. It may appear as a mathematical mess, but on the next slide we will try to take a closer look at it and make some sense of it. On the previous slide I showed you that we can write our signal as this Fourier series. Here I will try to show you what this pile of letters means. To help you understand this sum better, here I have wrote down a couple of these summands. For k is equal to 1, this will become this. We do not have the k of 2 because all the k's are odd, so the next k will be 3. And when k is equal to 3, this will become this. The next value of k will be 5, in which case this will become this. And now for the negative values of k, this is what we will get for k is equal to -1, this is what we will get for k is equal to -3, and this is what we will get for k is equal to -5. Last, when k is equal to 0, that is not included in this sum, that is what we have included separately, and that is this. So this 1/2 is what we get when k is equal to 0. Now, let's see what happens when I add this complex exponential to this complex exponential. When you take a look at them, you should be able to identify that the sum of these two complex exponentials is actually this cosine. So when I sum these elements for k -1 and 1, I will get this cosine. And this cosine I have plotted here. Now what happens when I add this exponential and this exponential? Well, first I should turn this complex amplitude into a proper polar form of a complex number. A proper polar form of the complex number will have the magnitude here, which is positive, and then this minus sign will be expressed as e to the j pi. This e to the j pi is equal to -1, and that is what will create this minus here. The same thing can actually be done here, so when you combine this entire complex exponential and this entire complex exponential, you will actually get this cosine. This cosine I have plotted here. Here you can actually see that phase shift by pi, this phase shift. And last, what happens when I combine this exponential with this exponential? Well, they will give me this cosine. This cosine I have plotted here. And in this fashion I could go on combining the exponential for some positive value of k and the same negative value of k, and each time I would end up with some cosine with a certain amplitude and a phase shift. For example, for k7 and -7 I would get this cosine. A slight irregularity appears to be the case when k is equal to 0. Here I do not have a cosine, I just have a constant. But in truth, a constant is just a cosine at 0 frequency. A cosine of 0 is 1, and when I multiply that by some amplitude, I can get whatever constant I want. This constant I have actually plotted here. Now, this expression tells me that I should add up this constant and all of these cosines. Of course, there is going to be an infinite number of these cosines. But here, just for illustration, I took these 5 functions and I added them together. This is what I got. And you can see that when I add only these first 5 non-zero functions, I will get something which already starts to resemble my signal. Of course, this is not yet a perfect fit, but I still have infinitely many of cosines to add. If I added infinitely many of these cosines, I would actually get this signal. So this is the meaning of the complex Fourier series. This complex Fourier series actually hides these cosines, these pure tones, and when you add all of them together, you will get your signal. Now, we are often interested in the amplitudes and phases of these cosines that are included in our signal. The information about these amplitudes and these phases are hidden in the complex amplitudes, of these individual complex exponentials. On the previous slide, we have computed that for this signal, the complex amplitudes have this form. And this is what we also call the complex spectrum of our signal. If we are interested only in these magnitudes, we need to take the absolute value of this complex spectrum, and that will give us the amplitude, or sometimes we call it the magnitude spectrum. So what are the magnitudes of these numbers? Well, for k even and 0, the magnitude is 0. In this case, when k is odd, it will be 1 over pi k, and for k is equal to 0, it is 1/2. So the magnitude can be written like this when k is equal to 0. Check that out. When k is even, this will become 1, and 1 minus 1 will be 0, so this entire thing will be 0. Thus, for k even, we will get this 0 as we should. Now, when this k is odd, this entire thing will be minus 1. So 1 minus 1 will give us 2, thus this entire expression will be 1 over pi k. That is the absolute value of this expression for k odd. And last, for k is equal to 0, 1/2 really is the absolute value of 1/2. So this is the expression for the magnitude spectrum of our signal. Here I have it plotted. For k is equal to 0, I have the value of 1/2, which corresponds to this 1/2, this 1/2. For k is equal to 1, we will get this value, which corresponds to this 1 over pi. For k is equal to 3, we will get this value, and that corresponds to 1 over 3 pi. For k is equal to 5, we will get this value, and that corresponds to 1 over 5 pi. For k is equal to minus 1, this value corresponds to this 1 over pi. For k is equal to minus 3, this value corresponds to this 1 over 3 pi. So you can see that we have both positive and negative k's. That means that we have both positive and negative frequencies. The reason for this is that we work with complex exponentials, and it takes two complex exponentials to create a cosine. One will be at a positive frequency and the other will be at the same negative frequency. Now, the phase spectrum. The phase spectrum is the phase of these complex amplitudes. The phase of these complex amplitudes, for example, for k is equal to minus 3, that would be the phase of this complex number. That would be this pi. And that also corresponds to the phase of this cosine. So if I treat these values as complex numbers, what are their phases? Well, 1/2 is a positive real number, so its phase will be 0. 0 can have pretty much any phase, and we will set it to 0. Now, these numbers can be both positive and negative. When I get a positive number here, its phase will be 0. But when I get a negative number here, I need to treat it in this fashion. Its phase will be pi. Note that this phase can also be minus pi. E to the j pi is minus 1, and e to the minus j pi is also minus 1. So a real negative number can have phase which is either pi or minus pi. That is the same thing. When I put it all together, the phase of these numbers, that is the phase spectrum, can be expressed as either pi or minus pi when k is odd and k minus 1 over 2 is also odd. In that case, this has negative sign. And in any other case, these values are either positive real numbers or zeros, so their phase will be 0. Consequently, this will be the phase spectrum of my signal. When I plot it, I will get this. I've chosen to use positive values of pi for positive k and negative values of pi for negative k. Later on you will see why I'm doing it like this. So this plot tells me how these complex exponentials are phase shifted, how these cosines are phase shifted, how my tones are phase shifted. To summarize, in this lecture I have introduced the concept of the time domain and the spectral domain. If we take a sound as an example, the time domain would be how a microphone records a sound. The spectral domain would be how our ear perceives the sound. And I also told you that when we want to get from the time domain to the spectral domain, we use the Fourier transform. And in the inverse direction, we use the inverse Fourier transform. In this lecture, I told you about one of the 4 types of the Fourier transform, the Fourier Series. This expression will allow you to turn the signal in the time domain into the description in the spectral domain. this is the complex spectrum that can tell us what are the amplitudes of the individual frequencies our signal is composed of. Also, this complex spectrum contains the information about the phase at those individual frequencies. This complex spectrum also goes under another name. These C sub k are called the coefficients of the Fourier series. The Fourier series is this expression. It is the sum of the series of exponentials with complex amplitudes given by the spectrum of the signal. And the sum of the Fourier series allows us to turn the spectrum, that is the description of the signal in the spectral domain, into the signal in the time domain. So this is a form of the forward Fourier transform, and this is a form of the inverse Fourier transform. Now just a few properties of the Fourier series. The Fourier series was developed for continuous time periodic signals. And note that the spectrum of the Fourier series is discrete and aperiodic. The spectrum of the Fourier series is discrete and aperiodic. And one more thing, this is how we compute the spectrum for index k. Now, this is how we compute the spectrum for the index minus k. Note that when I go from k to minus k, the only change that will happen is that this minus will go away. Consequently, if this signal is real, this expression is going to be the complex conjugate of this one. Therefore, for the real signals, the spectrum for some index minus k will be the same as the spectrum for the index k except complex conjugate. That also means that the magnitude spectrum for some index minus k will be the same as the magnitude spectrum for that index k. The complex conjugation does not have any effect on the magnitude of the complex number. But what the complex conjugation has effect on is the phase of a complex number. Therefore, the phase spectrum for some index minus k will be equal to the minus of the phase spectrum for that index k. And you can see that here, this is a real signal. Therefore, we have this symmetry in the magnitude spectrum. The value for some negative k is the same as the value for the same positive k. Mathematically, that corresponds to this. And in the phase spectrum, the value for some negative k will be negative of the value for the same positive k. Mathematically, we can write that like this. Just let me stress out that this holds for the real signals. If the signal in the time domain is complex, this symmetry is broken.